basic structure of metals and alloys, oxide and its oxidation will be discussed. So, defect structure of metal, oxide and oxidation. Now, whenever we see a metal is getting oxidized, so this is metal side, this is let us say MO, where the stoichiometry is 1:1, and then you have oxygen environment. So, this is oxide environment interface, and this is metal oxide interface. We see that the simplistic approach in order to understand how the oxidation is taking place, and this is already discussed while discussing the similarity between oxidation and electrochemical corrosion phenomena. So, we have M releasing 2 electron going to M2 plus, which is anodic reaction. So, this is anode, and now this one diffuses through the metal oxide and reaches to this oxide environment interface, and at the same time this 2 electron will also reach to the other end, and that means oxide is acting as conductor because it is also transmitting electron from one end to the other end, and these 2 electron oxygen adsorbed oxygen will accept these 2 electrons, which is basically a reduction process, and go to oxygen 2 minus, and this is reduction. So, this is cathodic side, which is cathode, this interface is cathode. So, now this one will react with metal plus plus and then form metal oxide. So, we see this oxide, it also will act as electrolyte, since we are seeing that the ion transmission from one end to another end is taking place through the metal oxide. So, it is acting as conductor as well as electrolyte. Now, we are in this case oxide growth will take place on this end, but if other way around, if we see that this one transmits through this oxide layer and comes here, and then here 2 plus plus O minus reacts and then form MO. So, the oxide growth will take place on this end. So, that means whenever we see that metal ion goes to the anode surface to the cathode surface, that time oxide growth is taking place on this end, that means on the oxide environment interface, and if oxygen is coming here and then on the metal oxide interface, oxide growth is taking place. Now, there could be a simple experiment which can tell you that which is the governing factor or which interface is actually growing, and also we see that, and that process is called platinum, that is called a kind of noble metal, attaching a noble metal wire before the oxidation on the metal surface and seeing the position of that noble metal wire on the oxide surface after oxidation rather. So, that is basically the marker experiment. So, if we do marker experiment, marker experiment. So, that case let us say this is the metal surface, this surface is getting oxidized, this surface, and on this surface let us say we put some platinum wire marker, this is platinum wire marker, and then we are exposing it to oxidation and seeing that what would be the position of this marker after oxidation. So, then we can see two situations. One is, let us say if this is metal, in this case this is metal and these are markers which are platinum markers, which are platinum wire. Now, let us say after oxidation we see that the platinum wire is basically on top of this oxide layer, and now this is MO and this is O2 gas. If the platinum marker on top of the oxide outside, these platinum markers are basically on the outside of the surface which is getting oxidized, then we can tell that the oxidation growth is taking place on this surface. Oxidation growth is taking place on this surface. That means, this is happening due to inward diffusion of oxygen. Now, similarly, if we see on the same diagram, if we see that so another case would be, if we consider that this is the other surface, the inside surface, and if we see that those platinum wires are basically on the inside surface, this is the platinum wire position, this is another position, this is another position. So, we have the platinum wire actually is position wires are on the inside surface of the inside surface after oxidation, and that means this is on the surface between metal and metal oxide. That time the second case, this is first case, second case the oxidation growth is taking place on this end. Oxidation growth is taking place on this end. Now, that means this is generally this is happening because of metal cation diffusing outward. Outward means metal oxide to metal oxygen interface. So, from the position of this marker we can clearly tell that where the oxidation is actually where the oxide is actually growing. Now, this marker experiment would definitely depend on the reactivity of the marker with the metal oxide or metal, and because this reaction, this process is generally taking place at higher temperature, as well as thickness of this or the diameter of the wire. Now, if the diameter of the wire is more than the thickness of the oxide layer, then it would not give any indication that where the oxide growth is taking place. Now, from this marker experiment, it is very clear that there is a diffusion of oxygen anion or metal cation through the oxide layer, and the diffusion is due to the defect structure of the metal oxide. Now, let us see what are the defects in the metal oxide. Defects in metal oxide. So, generally we see that in solid we have 4 types of defects. So, we have 4 types of defects. One is point defect, and example of point defect is vacancy or interstitial, atom, or in case of oxide it would be cation or anion in case of oxide. Then we have line defect. One example of line defect is dislocation. Then we have surface defect. Example of surface defect, grain boundary, or any surface, and of course, there could be a volume defect. Example of volume defect could be void. So, we have 4 kinds of defects in solid. Now, our primary interest would be the point defect in oxides. So, let us discuss what are the point defects, common point defects, which are important for our current discussion. So, let us discuss point defect in oxides. And before coming to the point defects, we know that the point defect is thermodynamically stable consideration, and the amount of point defect that exists in a particular solid, that would be determined from this formula minus del H V R T, where this is Avogadro number and this is number of point defect. This is the molar energy for formation of that point defect. R is gas constant and T is basically the temperature in Kelvin. So, this from this we can determine what is the percentage of or the fraction of point defect that exists in a particular solid. In the oxide also this formula is well valid. Now, in most of the oxides, they are generally ionic in nature. So, now if we consider ionic oxide, that means they have cation site and they have anion site. So, but one particular consideration in case of ionic oxide, there we always see that the sum of charge, cationic charges would be equal to sum of anionic charges and of course, it will maintain electroneutrality. So, the electroneutrality would be maintained. Now, in case of oxide, we can divide the defects in oxides, we can divide them into, or the point defects in oxides, we can divide into two segments. One is stoichiometric defect, and then we have non-stoichiometric defect. But they are in stoichiometric defect, there are two major defects. One is Schottky and another one is Frenkel defect. Now, in case of non-stoichiometric defect, we have many varieties. Out of that, we would only consider two major varieties, and those will lead to, one is p type defects, p type oxide, the another one is n type oxide, and p type where the charge carrier is basically the hole, and in n type charge carrier is electron. So, now let us see what is Schottky and what is Frenkel, and also what is stoichiometric defect. In case of stoichiometric defect, generally the anion and cation concentration are maintained constant. So, stoichiometry means, let us say one metal oxide is denoted like this MO, and where cation and anion ratio is 1:1, and this will always maintain 1:1. So, this is called stoichiometry in oxide, or it is stoichiometric oxide. Now, in this case we have Schottky defect. Schottky defect, for example, if we have anion, let us say the negative is anion and there is a small one positive which is cation. So, like that we can have distribution like this, then we have like that, we can let us say this is a simplistic form of that oxide lattice. Now, where we have let me extend it by one more layer. Like this. So, we see that there is a small part of that particular oxide where we have the same number of cation and same number of anion. So, I think in order to make it same 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2, 3, 4, 5. ठीक है. So, 10. So, the total electron neutrality is maintained, and the Schottky defect, in that case one anion would be missing, one cation would be missing, cation from its normal lattice site it would be missing, and one anion would be missing. So, if we remove these two, that means there would be a cation vacancy and there would be one anion vacancy, and that creates the Schottky defect. So, that means this is my defect. So, the defect is basically you have vacancy of cation. Let us say the cation is denoted as X, and vacancy of cation is denoted, anion is denoted as X, and cation is denoted as M. So, you have vacancy of cation, same number of cation and same number of anion, both are missing from their normal lattice points, and so the overall MO, and in this case actually MO is maintained. Now, if this is double charges, so if we have double charges there, so even if we miss one and one there, one cation and another anion, so overall this 1:1 stoichiometry is maintained. At the same time, you see that overall electroneutrality is also maintained. This is Schottky defect, that means the equivalent amount of metal, cation and anion are missing. Now, this is Schottky defect. Then we have Frenkel defect. In case of Frenkel defect, there, and let us come to the same diagram. If we consider Frenkel, now we put all those points again, all those cation and anion. Now, that case, since cationic size is smaller than anionic size, so then there could be a vacancy which is created here, and then that cation will come and sit here in the interstices. So, this is basically, this cation has moved to the interstices position, which is basically the interstitial position of all 4 atoms, 4 ions, and it is basically a vacant site. So, this is my Frenkel defect. So, if in case of Frenkel defect, no cation and anions are missing, actually the missing site, the cation which is basically missing from the normal lattice site, that cation will go and sit in the interstitial position, and then it will give you Frenkel defect. Now, coming to the non-stoichiometric defect, and before we come to the non-stoichiometric defect, let me tell you this stoichiometric defects. Stoichiometry is very hard to be found because thermodynamically they are unstable. So, in order to explain the oxidation behavior of metal, we need to concentrate more on non-stoichiometric defects. So, non-stoichiometric defect so one could be p type. So, the p type defects are basically either it could be metal excess, where X is anion and M is cation in the lattice. So, this is metal excess, or there could be oxygen deficient oxides 1, two minus delta. So, this is M X 2 minus delta. So, they form N type oxide. So, that one example is, for example, if we consider this one, that time the example is zinc oxide, or it could be this one where we have Zr O2. This is another one example. This is zirconium oxide. Now, let us see the defect structure of ZNO. Now, if we consider the defect structure of ZNO, then we can have a small part of the lattice in 2 dimension. So, Zn plus plus O minus minus. So, like that we can have distribution. If we consider this, and since we have the common formula would be Zn 1 plus delta O. So, that means there would be excess cation. So, excess cation, let us say there are 2 excess cation and those will be in the interstitial position. So, here is 1 and here is 1. So, these are the 2 excess cation. Now, if we have 2 excess cation, then in order to maintain electron neutrality, there will be excess electron, 4 excess electron. This is basically a simplistic approach, and this would be sufficient for our understanding on the oxidation behavior of zinc oxide. So, this is these are 2 cations in the interstitial position, and there will be 4 electrons which will neutralize the entire system, and this here the charge carriers those electrons. So, the charge carrier in this case electrons, and that is what this is called N type. And then if we try to find out the diffusing species for the oxidation, here the diffusing species is the interstitial zinc plus plus, which will off, and then this will come to this position, this will come to like that, this will try to move, and if we consider this is metal surface and this is oxygen surface, then this way the diffusion would take place. So, the interstitial movement of atoms, interstitial movement of those cations would be the diffusion control step, and the charge carrier is basically the electron, and this is N type oxide. And another stoichiometric defect which is P type, and there we can also have the demonstration of P type oxide. In case of P type oxide, either we have metal deficient and this is cation, this is metal, or we can have oxygen excess or a cation excess. So, 2 plus delta. One example is uranium oxide, and this example is nickel O, NiO, FeO, like those are the oxides which have P type structure. So, in this case the charge carrier is hole, electron hole, and the diffusion is happening through the movement of metal ion vacancy. So, how does it happen? Let us see that. So, that case we have NiO, Ni plus plus O minus minus, Ni plus plus, O minus minus. So, let me draw the full structure. So, this is O, this is also a system simplistic representation of this oxide in 2 dimension. And now we see here the oxide non-stoichiometry is like this, Ni 1 minus delta O. So, that means there would be missing nickel cation sites. So, if we have 2 missing nickel cation sites, so that means 2 vacancies are created. Now, in order to, so that means we have 2 extra anions in the system, 2 extra negative charges in the system. So, in order to balance those 2 extra, rather 4 extra positive negative charges, that means these 2 nickel, here we have 1 nickel cation, here another nickel cation, both 2 nickel cations are missing, that means 4 negative charges would be extra. So, in order to neutralize those 4 negative charges, there would be a hole creation, this is hole. So, that means nickel in the normal site would ionize and form the hole. So, there will be 4 hole, this is 1, 2, 3, 1, 2, 3, 4. So, the 4 holes are created. So, it is a balanced. So, this is here the charge carrier is electron hole, and diffusion is basically by through this vacant cationic site. So, this is the p type oxide, which is nickel oxide or iron oxide. Now, once we know this 2 types of oxides, then we can also explain in case of p type as well as n type how the oxidation is taking place. Let us try to understand that. So, the oxidation mode in p type and n type. Let us say we consider oxidation of metal excess oxide. So, zinc oxide, where we have excess metal cation in the interstitial position. So, there if we see the schematic representation, so this is oxide and this is zinc, this is O2, and there we have anion anodic reaction on this surface, which is metal oxide surface, metal oxide interface, metal oxide interface, there we have anodic reaction, and then this 2 electron will go through electronic conduction will happen, and then this electron will go to the other side, and then oxygen will accept 2 electron and convert to oxygen 2 minus, which is cathodic reaction, and this metal cation will again diffuse through the metal oxide layer by the mechanism of interstitial diffusion, and it will reach to this surface, and then these 2 will react and form metal oxide. So, your oxidation growth is taking place on this surface. So, this is in case of oxide with excess cation or N type oxide. Now, there could be also a possibility of N type oxide with oxygen deficiency. So, it could be ZR let us say metal O1 minus delta. So, there we have oxygen deficiency. We can also have a sort of atomic movement, ionic movement as well as electron transfer, and we can also explain how the oxidation is taking place, but there we have oxygen vacancies. So, the diffusion would be of the oxygen anion to this surface. So, in this case we have oxygen vacancies. So, that means if we have oxygen vacancies, that oxygen vacancies will try to, now this is the second case where you have less oxygen in the lattice. So, you have oxygen vacancies. So, the oxygen vacancies, through the oxygen vacancies we have oxygen anion movement or the diffusion on to this surface, to this section. This will go this way, vacancy will go, the oxygen vacancy will go this way, and on that way oxygen anion will come this way. So, oxygen anion will come to this surface, but rest of the thing would be same, and here oxygen anion will react with 2 plus, because there is no cation interstitial, only the anion vacancy. So, the anion vacancy will move to this side and anion will move to this surface. So, here the reaction would happen, that means cation and anion will react and form MO. So, the second case, the oxidation growth will take place on this surface, on this surface. So, this is the explanation of oxidation in case of N type oxides, where either you can have excess metal in the interstitial position or oxygen vacancy. So, let us also look at what happens in case of P type oxide, and we see in case of N type oxide that oxide growth would be at two different interfaces depending on whether it is metal excess N type oxide or oxygen deficient N type oxide. Now, in case of P type oxide, let us consider metal in case of N type metal excess oxide or oxygen deficient, but in case of P type let us see what happens in case of metal deficient P type oxide. So, if we see the metal deficient P type oxide, how the growth is taking place. So, we can have another two different interfaces. Let me draw it in a, this is metal, this is metal oxide and this is oxygen. Now, same thing, this side anodic reaction would happen. Now, this since this is this kind of oxide, so we have vacancies, cationic vacancies. So, this will this metal cations which are forming due to anodic reaction at this interface would try to diffuse through the oxide by the interchange of by the collective diffusion or the of metal vacancies. So, the metal cation vacancies are also moving this way, and due to this process this is diffusing from this interface to that interface. Now, these 2 electron will come here and this electron would move to the other end, and here oxygen will accept 2 electron and then form oxygen anion, and by the time you have presence of metal cation on this interface. So, this 2 will react and form MO. So, the metal oxide growth would be at this interface, but this electron transfer which is taking place here is not what we have seen in case of N type oxide. The electron transfer is taking place by exchange of electrons via the electron hole, through the electron hole. How the exchange of electron through the electron hole that is taking place, let us see that process. Now, here we have 2 electrons which are coming through the metal to the other section. Now, if we consider here what happens, metal and so also we have hole here. So, hole will try to move this way and electron will try to move this way. So, now there will be hole and electron interaction. So, we have hole which is nothing but M plus plus plus, this is actually hole, plus E which will form M plus 2. So, that means due to this interaction, hole and electron interaction, which is basically the trivalent metal cation reacting with electron and forming M2 plus. Now, again this M2 plus, so electron has come from this to this point. Now, again M2 plus will one electron will be removed from M2 plus. So, another hole will be formed. So, this will form another hole. So, and this hole will also again react with electron and form metal 2 plus again, and then this will again one electron will be again taken out. So, this part is, if we consider only this part, so again it will form hole, and we have seen the hole is nothing but metal cation. So, we see that electron is moving from this end to the other end due to the interaction with hole, and the reaction nature is like this. So, there would be always exchange like this. So, there would be always exchange like this. So, due to this exchange, electron is moving from this end to the another end due to the exchange, due to the interaction between hole and electron, and so finally, we have electron reaching there. So, this electron is actually on this surface, and gradually we have more and more electrons which are coming at this surface, which will form, which will favor this reaction, which is cathodic reaction. So, the oxide growth is taking place here. Now, we see that the hole is also moving this way. There could be a possibility, and this metal cation diffusion is taking place through the hole metal cation interaction, and this hole, couple of holes, they can combine and they can form a pore here. So, this is pore. So, one pore can be created due to the interaction or combination of many holes, and this is the mechanism how the pore forms in p type oxide. So, this is one example how the oxide growth is taking place in case of p type oxide, where we have metal cation deficiency, and also we have seen in case of n type how the oxide growth is taking place. Now, let us come to, since we have seen the oxide structure in case of p type, which is nickel oxide, or in case of n type, which is zinc oxide. So, if we dope them with a cation with a less valency than the metal cation in the normal lattice point, or replacing the normal lattice point cation with another cation which has more valency than the cation which is being replaced. So, what would happen in case of, what would happen to the oxidation of that metal. Now, let us first come to zinc oxide. In case of zinc oxide, we see that the oxide structure is like this. Let us replace one of the zinc cation from the normal lattice point with a lithium cation. Another one, let us replace with lithium cation, and we can also replace one more cation with lithium plus. So, that means we are replacing 3 zinc cations with monovalent lithium cations. Now, that case, what would be the nature of this structure? So, now that case we see that if we have 3 lithium cations which are replacing 3 zinc cations. So, we see that there would be 3 excess negative ions. Now, that case, in order to balance that 3 excess negative ions, negative charges, not ions, negative charges, then if we increase one interstitial cation, then we see that there is one more negative charge which is to be neutralized. So, in order to neutralize that one more negative charge, we can get rid of one extra electron. So, we see that now this is neutralized. So, that means the entire oxide is neutral. So, that case we see that number of cation interstices are increases. So, cation interstitials are increasing, number of cation interstitials is increasing. So, we have 5 cation interstitials, previously it was 4 cation interstitials and 3 extra electrons. So, the charge carriers concentration is decreasing, but the interstitial atom cation concentration is increasing, and the diffusion is taking place by the movement of this interstitial cation through the interstitial positions. So, that means, if we replace zinc cation with lithium cation, then we have increased diffusion species. So, if we have increased diffusion species, of course, there is a decrease in charge carriers, but the diffusion is basically taking place via this interstitial diffusion. So, if we have increased diffusing species, so there would be more oxidation. So, if we replace zinc plus with lithium plus, we have increase in diffusion species, that means increase in cation interstitial, we have more oxidation, that means oxidation resistance would decrease. Now, let the situation be like this. Let the situation be like this. So, zinc cation. So, 3 zinc cation is replaced by 3 aluminum cations. So, that means we have 3 extra positive charges. So, that case, in order to balance that 3 extra positive charges, we can, if we increase the electron content. So, if we make it 5 electrons, so that means we balance. So, that time this would be replaced by aluminum plus plus. So, that case if we make 5 electrons, so that means we see that 2 extra positive charges are remaining, which are to be balanced. So, now if we remove 2 positive zinc positive charges, so then we see that we have left with 1, we are left with 1 zinc cation in the interstitial position. So, that means in this case, and then you see that overall balance is done. Now, that case we see that in this case we see that total number of diffusing species decreasing, and hence oxidation resistance would increase. So, that means if we dope zinc oxide with aluminum, then we see that there is improvement in oxidation resistance. But if we dope zinc oxide with lithium plus, then the oxidation resistance will go down. Now, what would happen in case of nickel case? So, in case of nickel, if we replace 3 nickel cations from their normal lattice points with lithium plus, now that case we see that total number of negative charges. So, we are replacing nickel plus 3 with 3 Li plus. So, we say that 3 extra negative charges are there in this lattice. Now, if we replace one vacancy with nickel plus, then we are left with one negative charge, extra negative charge, and that extra negative charge can be balanced by forming one extra positive hole. So, then you see that the overall neutrality is maintained, charge neutrality is maintained. Now, in this structure we see that the vacancy concentration is decreasing. Vacancy concentration is decreasing, that means if we decrease this vacancy concentration, there would be less nickel plus diffusion through the oxide layer, and if there is less nickel plus diffusion, then my oxidation rate would increase, oxidation resistance would increase, Now, the situation, let us say I replace 3 nickel plus plus with 3 chromium plus plus plus. So, that case instead of lithium we put chromium and then one more place is here. So, that means here we have 3 extra positive charge. So, in order to balance that 3 extra positive charge we can create, there could be creation of more vacancies. So, we can create one more extra vacancies, this could be one more vacancies. So, we have 3 vacancies. So, if we have 3 vacancies, 3 vacancies, then one extra positive charge is still left. So, there could be left with one extra vacancy. So, one extra positive charge, and in order to balance that we can reduce the positive hole. So, if we reduce positive hole, we see that overall balance is maintained, charge neutrality is maintained. And that case, in this case we increase, this is first case, and the second case vacancy concentration increases, and if the vacancy concentration increases, that means diffusion of nickel plus plus would be faster, and if it is faster, then oxidation would be faster. So, resistance would go down. So, oxidation resistance would go down, but generally we see that the chromium addition is for improving the oxidation resistance of iron. That is true if the chromium content is beyond certain critical limit. Now, in case of doping, in order to have this benefit of doping, in order to have increased oxidation resistance, we need to dope it maximum up to 5%, but if it is beyond 5%, situation would be different. For example, in case of chromium addition, in FeO or iron, so there if chromium content is beyond 18%, so instead of FeO layer there could be a formation of Cr2O3 layer, and if the Cr2O3 layer forms on the surface, then it could give a very good oxidation resistance, rather there is a decrease in oxidation resistance. So, the chromium oxide layer would form, and that concentration is about 18% chromium in iron. So, that case chromium oxide would form on the surface, and it on the iron surface, and it could give a very high oxidation resistance.